Hello everyone, so my name is Shami
My name is Nigel.
and we will be participating in the science show, Retro Science Show competition.
Yeah, we have done a series of experiments that we hope you guys enjoy. Anything you want to add?
So yeah, we'll be doing experiments mostly related with cups and mostly just physics subtopics. So I hope you guys enjoy. Anything else?
No. Just, we hope that you guys actually learn a couple of things or so from our experiments. These experiments are very simple and can be carried out by anyone at all, anywhere. Alright, so we'll see you in a bit.
Alright, see you.
Alright, so for our first experiment, it's basically based on atmospheric pressure. So all you need for this experiment is three things. A cup filled with water and a card. It can be a card, a board, piece, or anything, just card in general. What we're going to do is going to put this on top here, on this cup filled with water, turn it upside down, and 3, 2, 1, it just sticks. Because this is based on atmospheric pressure. What you see is that the higher atmospheric pressure outside is actually pushing the card inwards, preventing the water from actually escaping outwards. Because, well, what you can say is that the water inside here in the cup has a lower atmospheric pressure compared to outside. So, by physics, it pushes it inwards. So yeah, and you can remove it, just... Thank you!
Alright, so for my first experiment, I'll be doing diffusion. Now, what is diffusion? Diffusion is the process whereby a substance, mainly I'll be using this, which is soy sauce, as an example, whereby how diffusion occurs. And this is my substance. Alright, so the substance, it will move from higher concentration gradient to the lower concentration gradient. It means that from high concentration of this to low concentration of this, which is nothing. So, to prove what I'm trying to prove here is that when I fill in some drops of soy sauce inside the water, it will unevenly separate throughout the whole water, meaning that it won't fully change the color of the water, but it will just be like the molecules of this will be spread throughout the water, and I'll prove it. I'll show it. So it's like this. Like that. Now this is what I'm talking about, as if you can see that there are some soy sauce on top on the, you can't quite see it, but you can see the color, like how it doesn't fully change the color of the water, but instead that it groups up under here. So what I'm trying to say is that diffusion occurs from this when I pour this inside, and it will spread throughout. It will spread throughout the water, meaning that, like I said, it will not fully change like this. It will not fully change the color of the water, but instead it will just have this shade of how it's trying to separate the molecules of this soy sauce. So if I put more, even more, and it's starting to change. The color is starting to change, and it's due to the amount of soy sauce I use. It will change. The diffusion will occur more rapidly due to how the concentration of soy sauce in here is increasing and increasing, thus making this a mixture of water and soy sauce. So, how is diffusion good for us? Why is it so important? Why am I doing an experiment of this? So the importance of diffusion is that without diffusion, I'll use respiration, as an example, during respiration is when the alveolus inside of our lungs needs to exchange gases, as in like when we exhale oxygen gas and then somehow carbon dioxide gas is exhaled out of our bodies, out of our mouth or our nose. So how does that happen? Because diffusion, more in a biological standpoint, simple diffusion occurs in the lungs, also or inside of the lungs. Yeah. So when we inhale oxygen gas, a very rapid, in a very split second, like right now I'm breathing, gaseous exchange occurs very rapidly. Means that the carbon dioxide inside of my body will be exchanged with the oxygen for it to use to become the energy for my body, and carbon dioxide gas will be exhaled out of my body because it is a very dangerous gas inside of our body if it accumulates inside us. So in short, what I'm trying to do here is that I'm trying to show why diffusion is important to us all, and how we should not just we should use this. Hold on. We should use this in our. We should use this more efficiently, more in a smart, use smartly, so that we can use it in our daily lives. Like example, maybe not really an example, but a situation. Like how can we smell the food our mothers make, or our dads make, from the kitchen to our room? This is because diffusion occurs throughout the atmosphere, inside, in the whatever the space here. So diffusion occurs due to the smell, the gas produced from the food, and it will just spread throughout the atmosphere, and giving it, and some of it will reach us, and we are able to smell it. So that's it for my experiment, and on to Nigel's.
Alright, so today we're going to do an experiment based on inertia. Now, inertia is basically everywhere in our lives, every day. For instance, when your car suddenly stops, you have the tendency to move forward. That's why we wear seatbelts, right? And, well, inertia originated from the Latin word of laziness. And the reason for that is because, well, the operational definition for inertia is the tendency of an object to maintain its state of rest, or if it's moving, to continue its motion in a straight line. So here today we have two experiments, so we're going to test out how inertia works. Alright, tell me when you're going to start. Alright, so right here we have a stack of books here, basically just normal school books here, and if you were to try to pull out a book from the middle very fast, you would see that the two books on top stays on its original position, because, well, like I said earlier, inertia is the tendency of an object to maintain its state of rest. In this case, these two books, the state of rest was on top, now it's in the bottom here. That's how it works. I feel like I should add on that inertia is also basically a factor affecting inertia. It's mass. The higher the mass, the higher the inertia. That's how it works. So if you had a train and a ship at sea, a very big ship, when they want to jolt to a stop, it will take a longer time due to their bigger mass. So yeah, so right here the books on top are definitely heavier than the book here. So that's why it stays at its position as well. So moving on to our second experiment, we have a cup here, a normal cup, plastic cup, a 50-cent coin, and a piece of paper. What we're going to do is we're going to put the paper on top here and a coin right here. If you watch closely at the coin, once we move this paper away, the coin has the tendency to fall into the cup. This is because, well, like I said earlier, inertia is the tendency to maintain its state of rest, which the coin is at just now. If it's moving, then it will just move in a straight line. That's how it works. So a factor affecting inertia is basically friction. If your frictional force is very big, then the inertia will be very small. That's how it works. And yeah, inertia can be applied
everywhere in our daily lives. That's like why when you're in a car, when the car is moving, we wear seatbelts for a reason. We have headrests at the back of our heads for a reason, to ensure that we're traveling at the same velocity. Because inertia will make you stay at your original position. So in the case of an accident or a sudden stop, you'll be protected by your seatbelts, by your headrest, and everything. So inertia is a very important factor in our daily lives, and yeah, these are just simple experiments you can prove how inertia is around you. Thank you.
As for our next experiment, I'll be doing on light. What is light? Light is a form of energy. That energy that is able to go everywhere in the atmosphere, as in like it gives us light source for us to see everywhere. Even in a dark place like this, we can just add a light source and it will become brighter. We are able to see more things. Like example, this place. If we shine a torchlight, we are able to see the insides of the cupboard, like me. Okay, so the experiment I'm trying to do today is that I want to show that the contradiction of light. Since light goes everywhere, it goes everywhere, but somehow it still travels in a straight line. I'll be examining this by using this a paper that I rolled up and then I taped it so that it roughly measures the diameter of the torchlight, and I'll be using a black backdrop to show how different the light is dispersed through, I guess. Alright, so firstly, as per usual, light. Okay, this is my light source, which is this torchlight. So when I turn it on, focus here, as you can see, it like focuses on one place, but yet it focuses on one spot and then it disperses throughout. But when I put this on, it is more concentrated, and you can see that the outlines, you can clearly see the outlines, and it's very, very focused on one point only, and it doesn't disperse throughout like that. So what I'm trying to say is that light travels in a straight line despite how messy it looks like how it disperses through everywhere. As you can see, the circle. And then, so that's how light works, I guess. How it keeps on, despite just goes everywhere, still travels in a straight line. And also, the reason why it spreads around like this, because that the light ray, I guess you can say, it's not only just one. It's just not only just one light ray. Not only one light ray, but it's actually very small. It's just a lot of lines. It's just lines of lights, I guess. Like it's just going everywhere. It's like this. Like yet again, like you can't see it, but I understand that light is like in a straight line, so it's like it disperses everywhere and creates this like effect of focus to effect, and then it fades.
Can light travel through mediums such as water?
Is it rolling? Alright, so
Can it travel through mediums such as water?
pause. And as for mediums such as like clear liquids, like example, this bottle of water filled like at least this much, you can still see how the light rays, it bounces off, it reflects into the bottle, and you can still see the reflection, the light going through the bottle. And yet again, there are some parts of the bottle that you can't see, which are these dark parts. It means that the light couldn't fully reach couldn't fully, I guess you can say, pierce through the bottle. So So in short, what I'm trying to say is that light goes in a straight line, and there are more than only one straight line which will be concentrated unless you add something to make it concentrated, like how this, and this one is the thing that that concentrates the light, the light from light source, yeah, the light source, like this. So yeah, that's all for today. Thank you, and see you next year. Never.